So we continue our look at op-amp parameters. Output resistance. The output resistance is the resistance R out viewed from the output terminal of the op-amp. Okay, and you can see they just included it in the standard schematic for a op-amp. Common mode input voltage range. All op-amps have limitations on the range of their voltages over which they will operate. The common mode input range voltage range is the range of input voltages which, when applied to both inputs, will not cause clipping or other output distortion. Many op-amps have common mode input voltage ranges of plus or minus 10 volts with a DC supply voltage of plus or minus 15 volts. Open loop voltage gain, A open loop. The open loop voltage gain of the op-amp is the internal voltage gain of the device and represents the ratio of output voltage to input voltage when there are no external components. The open loop voltage gain is set entirely by the internal design. Open loop voltage gain can range from 200,000 or more. Data sheets often refer to the open loop voltage gain as the large signal voltage gain. Okay, all of these things are typically going to be on the data sheets for the specific op-amp, and they're used by engineers, for real engineers, for design work. Common mode rejection ratio, then we've already taken a look at that, so you can review that dialogue there in your text. We've looked at an example of how to calculate the CMRR. You can go back to that and work on it if you wish. The slew rate, the maximum rate of change of the output voltage in response to a step input voltage, then, is the slew rate of an op-amp. The slew rate is dependent upon the high frequency response of the amplifier stages within an op-amp. High frequency response is limited only by the junction capacitances of the transistors. The low frequency response goes down to DC or 0 hertz because there are no coupling capacitors. Slew rate is measured with an op-amp connected as shown. Okay, so you can take a look at that. How do we calculate it mathematically? Well, the slew rate is the change in the output voltage over time, and we can see that by the graphs. Delta out is the maximum minus the minus max. Again, it's going to give you a sum there because of the change in sign. The unit of slew rate then is volts per microsecond. Example, the output voltage of a certain op-amp appears as shown in response to a step input. Determine the slew rate. So you can see what's going on here, the output versus time, and we've got a signal then, that an output that is being calculated here. The output goes from the lower to the upper limit, so in this case minus 10 to positive 10 in 1 microsecond. Okay, so we're within a range here beyond the curves where the linear range here on the graph. Since the response is not ideal, the limits are taken at the 90% points as indicated. Thus, the upper limit is 9 volts, the lower limit is minus 9 volts. Calculating the slew rate then, the difference then of 9 and minus 9 summed gives you 1 volt per microsecond. In a comparison of op-amp parameters, you can see here by type, they give you different parameters for different types of op-amps, and you can see what the comment section says to help guide you in selecting the correct op-amp for your purposes and design. Other features: most available op-amps have 3 input features: short circuit protection, no latch up, and input offset nulling. Short circuit protection keeps the circuit from being damaged if the output becomes shorted. No latch feature prevents the op-amp from hanging up on one input state, high or low, under certain input conditions, and the input offset nulling is achieved by an external potentiometer that sets the output voltage at precisely zero with zero input.